In this video, we're going to discuss about the energy in simple harmonic motion. So last time, we have discussed about the characteristics in order for you to say that it is simple harmonic motion. So for example, we have again the spring, and the spring here has a mass, and if you pull the string, we understand that there is a restoring force that is always towards the equilibrium. So if the mass is here, then that means that the restoring force is towards to the left, or negative of this, and we know that the force is equal to mass times acceleration, so that means that it's directly proportional to the acceleration, thus the acceleration is also negative. We understand that already, and thus we can conclude that acceleration is equal to negative of the displacement. And that means that it executes linear simple harmonic motion. We need to make sure that this system is frictionless, because if it is not frictionless, then that means that the amplitude here will be changing. But since this is just an SL class, then we don't worry about the damping. So we understand now that A means the amplitude. The amplitude is the maximum displacement from the equilibrium position. And we know that the period is the time it takes for one complete cycle. So for example, this is A, B, C, D, and E. If, for example, this mass, when you pull it and it goes back to this after a certain time, then that time is equal to the period, or capital T. Here we have letter A. This started here. Afterwards, we call this B, C, D, and E. We are having A, B, C, D, and E just for not for no confusion. So here we started from T is equal to 0, T over 4, T over 2, 3T over 2, and then we go back to T. We know that this is negative amplitude, and this is 0, and this is amplitude. So in this video, we're going to discuss about the energy in simple harmonic motion. But first, we need to make sure that there's a review here. Here, we have the position versus time graph. Sometimes we call this displacement versus time graph, or X versus time. It doesn't matter for as long as you understand it. So this is position versus time. This is amplitude. Here at position A, and then here B, C, D, and E. So we have already completed this one. So this is the period. Afterwards, we know that the velocity here at the start is 0. We know that. So we know that the velocity here is 0, as well as here at the left side, which is it is squeezed, and at the same time here in the last part. So we call this A, C, and D. So the velocity here is 0, but the velocity is maximum whenever that it is in the equilibrium position. Okay, you can also refer this as like a pendulum. So here we have negative because it's going to the left, and here we have D, which is going to the right, somewhere here. So we have the velocity versus time graph. All right, so why am I saying this? Because the velocity is related to, you know that it's related to kinetic energy. And what is the formula for kinetic energy? 1/2 mv squared. So if ever, of course, if ever that you know that velocity is 0, then that means that the kinetic energy is 0. So if where are the positions wherein the velocity is 0? At A, C, and E. So here we are going to do a graph for kinetic energy. And what is the kinetic energy here? This is the red part. So here at A, at C, and at E, we call this 0 kinetic energy because it is also 0 velocity. Now, we will proceed now here. This is the maximum. So the maximum will give us the maximum kinetic energy. So here and also here, the maximum kinetic energy. Notice that it does not matter whether it is positive and negative, because after all, it will be squared. And you know that energy is always positive in this particular case. Are we clear? All right, let's proceed. How about for potential energy? For potential energy, we know that it is also equal to, in the spring, we call it, the formula here is 1/2 kx squared, and the x there is the distance from the equilibrium position. So that means that if it's at the middle, then that means that there is no distance from the equilibrium position and the potential energy is 0. So where are those? It's the other way around. These are the B and the D. So at position B and D, the potential energy is 0. So we have here B and we have here D. But we know that if it has a maximum displacement, or like an amplitude, then we have a maximum potential energy somewhere like this, here and here, which we have A, C, and E. So we don't really care about the direction of this one, or the position, or whether it is positive or negative, because after all, it will be squared, and that means that it is still a positive one. And we know that energy here, this system, is always positive. We know also in topic 2 that conservation of energy. Conservation of energy means that energy cannot be created nor destroyed. It just changes from one form to another. So that means that in this position, we have potential energy plus kinetic energy is equal to total energy. So if the total energy is not changing, then that means that the graph here is this color green. For example, we have here the blue one, which is the potential energy plus the kinetic energy. We have this total energy. If we have here, then we have PE plus KE is also this one, and so on. So here, we have already discussed the graph for the simple graph for the energy in simple harmonic motion. If ever that you have questions, just feel free to give me a comment or send me a message, and so on. Thank you for listening and have a great day.